So this is Kailai from Stanford University, and is going to talk to us about calibrating multivariate Lévy processes with neural networks.
Yeah, thanks for the introduction. And I'm Kailai. I'm a PhD student in Stanford. And today we'll talk about calibrating multivariate Lévy processes using neural networks. So first, let me have a short introduction to what Lévy processes are. So the Gaussian processes are very useful in modeling many physical phenomena. About 100 years ago, the Brown proposed by many scientists, for example, the rapid Brown, who observed the random walk of it. The Brownian motion is a description of a random walk where the mean squared displacement is proportional to time. And the Gaussian processes is a Brownian motion with drifts, which are very useful in modeling many physical phenomena. But nowadays, as we have measurements, we found that an increasing number of electrical phenomena do not fit into this very relatively simple Brownian motion framework. And the mean squared displacement is proportional to t to the beta, where beta could be greater than 1, which is called super diffusion, or less than 1, which is called the subdiffusion. And the Lévy processes are mathematical tools that have been used widely to generalize Gaussian processes by allowing a heavy tilt step-length distribution in a random walk. They are very useful in describing those kind of anonymous diffusion processes. There have been already a lot of applications. For example, in biology, people have been using Lévy processes to describe bird flocking and also predators' movement patterns. And in mathematical finance, people use the Lévy processes to model the stock price. And also in solid mechanics, there are many applications for describing the fracture process. For example, the so-called paradynamics is one of the two that use this kind of Lévy process or non-local diffusion processes to describe the behavior of the materials. The one nice property of the Lévy processes is that it has a very less mathematical property, and the definition of Lévy processes is actually very straightforward going from the processes. It adds a jump diffusion process to Gaussian processes, which is here, and a sequence of random variables, and for this kind of a processes, the characteristic functions can be written as follows. Well, the first term is the drift term, usually you say in the Gaussian processes, and the second term is the diffusion term, and also the third term is integral response to this jump diffusion term. And as you can see that we can describe this Lévy processes using 3 parameters. The parameter is the second parameter is diffusion, and the third parameter is the jump. And for describing the jump, we usually need a function instead of some parameter. And this jump distribution, it can be non-smooth, and also it can also be delta distribution. So eventually, we want to use this mathematical tool to make a prediction. And that is, we know the drift term, we know the diffusion term, we also know the jump term, and we want to make a prediction of the time series. But typically, for many new physical phenomena, we do not know those kind of parameters beforehand, or it is very hard to model them. So we have to find them from data. Usually, we only have a finite number of data, but we want to estimate these 3 parameters, which is essentially an infinite dimensional mathematical object because we have an unknown function here. So this is a major challenge for predicting, for doing inverse problems on this kind of Lévy processes. Our proposed approach is to reduce the problem to a finite dimensional problem by applying some regularization using basis functions. For example, here, because the major challenge is the jump diffusion, is the jump distribution. So we approximate it by a parameterized function form, which can be parameterized by piecewise linear functions or radial basis functions. And particularly in this work, we consider the neural networks because for this work, the UX can be very special and it may be discontinuous, or we have a lot of noise in our data, which makes the traditional basis functions very challenging. And then the idea is very straightforward. If we already know this UX, we can just do on this analytical characteristic functions. So we have this kind of a numerical characteristic functions. And on the other hand, we have the data to compute the numerical, compute the empirical characteristic of functions. And we have formulated the squared loss using the numerical characteristic function and also the empirical loss function. We can then minimize this loss function using a gradient-based method, which in our case is actually automatic differentiation-based optimizer. You can see this as a stacking of a neural network with a numerical quadrature scheme, and then you optimize that using the data. Okay, so the special thing about our problem is that UX is non-smooth. And if we apply the traditional basis functions, such as radial basis functions, we will see a lot of difficulty here. For example, the radial basis function is not very good at approximating this kind of discontinuities. And for piecewise linear functions, because we very local base, very many local bases, so if we have enough data, we cannot fit piecewise linear functions very well. But neural networks is that it's it's in the middle of piecewise linear functions basis function. So and we have this kind of good properties for neural networks. So finally, I will present the applications. The first application is the alpha stable process, which is a special kind of Lévy processes. We want to estimate the jump parameter and also and we have two cases. The first case is where we have continuous functions, and you can see that for neural networks, it fitted very well. But for radial basis functions, as expected, it cannot deal with this discontinuity very well. Even for a smooth function, we see some difficulty for radial basis functions. This is because we are not doing a X to Y supervised learning, but we have to stack all the neural networks into a numerical scheme, and that brings some noise into the data. So that's why we see the difficulty for the radial basis functions. And we apply this approach to the financial data, which is the stock data pairs, and this is the alpha parameter here, and the second is gamma here, and we can see we can discover some patterns between the pairs, and you can see the peaks here. Those are discovered automatically using this approach. Okay, I think I reached the end of my talk, and I would like to introduce the software we use for this work, and it's called ADCME, which is inverse modeling library for scientific machine learning, and it's actually based on automatic differentiation and joint, and so you can use numerical schemes and quadrature rules, and as well as neural networks in a single framework. And for this Lévy processes work, we combine these two. We combine the neural networks and the numerical schemes in a single framework, and do the gradient-based optimization using this software. Yeah, I think I finished the talk earlier, right? Yeah.
I see that there's some questions that you answer. Would you like to tell us a little bit about that?
Oh, okay, sure. Yeah, that's about alpha. And typically for calibrating those parameters using the other methods, you shows that if alpha is very close to 2, which, well, the alpha usually lies between 0 and 2. If alpha is close to 2, you have a great difficulty calibrating that. But actually for this approach, we did not see much difficulty estimating alpha for those close to 1 or close to 0 or close to 2. I think the reason is because we discretize that using a quadrature rule, and that can be very accurate to capture those alphas.